you all for joining in. And I'm Tarun. I'm a co-founder and the CTO of ThirdAI, and I'm really glad to have you all in our second webinar. With me, I have our engineers, Benito and David, who would also be talking about some of the cool technologies that we have been building over the past 1 year. For the uninitiated or for people who didn't know about us until recently, ThirdAI is a very early stage startup. We are based out of Houston, Texas, and we started almost exactly a year ago with a mission to democratize AI to all CPUs, or all hardware. And to that effect, we have built a deep learning engine called Bolt. Bolt engine that is very performant. It trains and infers on any general purpose CPU at speeds that match or sometimes even surpass GPUs without any loss in accuracy. So and we do this across a multitude of tasks. So that is what we're going to talk about today. So the agenda for today is I'm going to get started with an overview of ThirdAI's mission, as in what we do, why we do, and how we do. And then our engineers are going to talk about some of the new out-of-the-box capabilities that we built. We are going to have a few cool live demos. Just to give a perspective, in our first webinar earlier this year, our emphasis was to show how performant Bolt engine is. How do we define models in Bolt engine? How do we train in like few minutes? How do we infer in in a millisecond? And how do we use our question answering system or something like that? The emphasis of this webinar is to show how easy to use our products are. Over the past few months, we have been working on building efficient data pipelines and auto-tuning all of our models and giving you out-of-the-box solutions. So even people without much background in deep learning who just know what problem they want to solve and what data they have can use our solutions with hardly 10-line scripts or something like that. So that is what we are getting at with this out-of-the-box capabilities. So, and at the end of it, we'll have a 5-minute Q&A session, and please feel free to chime in your questions through the talk, and we are going to address them at the end of the talk. Okay, so yeah, first, so to give an overview of what ThirdAI is, most of you might be familiar with this engineering barrier in AI. That is, most applications and pipelines reside on CPUs, but just the AI component of it has to be done on a GPU. So just to be a little more clear, we keep getting new data and we want to train our models on a regular basis. If you do not train a model on a regular basis, it drifts away and it becomes obsolete pretty soon in most applications. So to train a model, we need sophisticated hardware like GPU. So we push our data from CPUs to GPUs and then train a model and then redeploy the model that is trained on GPU back onto CPU for real-time inference and rendering onto a web page or something like that. So this loop is a bit of a barrier. That is, we always have to keep pushing our data to a new machine, train and redeploy. Now, this inefficient pipeline is what people have been trying to break in the last few years. And to a small extent, some companies, particularly in the last 3 to 4 years, have solved some of the redeployment problem. That is, they take a model that is trained on a GPU machine, and they use some primitive techniques like pruning and quantization and make it deployable on CPUs. But no one has figured out a way, how do we solve the retraining problem? How do we break this entire cycle of sending it to GPU and getting it back? And that is where ThirdAI comes into picture. So what we do, what we propose is that we say you do not need GPUs to train or infer your deep learning models. You can train large performant deep learning models on CPUs. Now that puts a lot of the barriers out of the scope, and then you have the capability to train wherever you have the data. You don't need to move things here and there. And what we believe is, due to the barrier that we just quoted, there has only been about 30% penetration of AI into problems that it can solve. With what we are proposing, we believe that all the problems that are conducive to AI will now start using AI. All that you need is to have a reasonable data set and a reasonable CPU machine to run your models. So that's where we break this barrier and create a new ecosystem of a lot of AI applications. Okay, so just in a nutshell, our Bolt engine is faster, and of course cost efficient because we only need CPU machines. It gets to comparable accuracy, and in fact sometimes surpasses GPU's accuracies with the same same speed or faster. We do not differentiate between different types of CPUs. We support x86, we support ARM, we support Apple's M1 or AWS Graviton or whatever new CPUs that may come tomorrow. And also, we also enable miniaturization and IoT. As in, since we are very efficient on CPUs, we can use a lot of low power machines to solve bigger problems. We can distribute the training, we can distribute inference, we can do training on edge devices and all of that. So that's what our capabilities are. Okay, so this is about what we do and why we do things, but how we accomplish the claims that we make. So that is where we have something called a sparsity knob. Now, just to explain what the sparsity knob is, we have a case study of an image classification challenge. So we get an image of a cat and we have to predict that it is a cat. Now, if you misclassify a cat as a dog, obviously you have to make updates to your parameters to correct it the next time. So on the left side, what we are showing is a dense update pattern that requires a GPU. On the right side, it is a network, the same network that is trained on Bolt engine that only updates few parameters for every sample. And that is done in a sparse way, in an adaptive sparse way. That is, every input has its own sparse pattern. And thereby we get we throw away a lot of computations and we still get the same accuracy. Now, the dark blue neurons shown here correspond to high activations for a particular image, and the lighter blue ones correspond to low activations, as in less relevant to the input image. Now, for any image in general across the network, we may have very few activations that are very closely relevant to the image, and a lot of activations that are not really relevant to that particular image. So what Bolt engine does is it just throws away all those light blue activation updates, and we don't even compute them, we don't even update them, and that's how we get the gains that we have been claiming. So just to see that in effect, how productive it can be in terms of many fronts. On the left side, what we are trying to show is that the two popular libraries in deep learning, PyTorch and TensorFlow, they operate at 100% sparsity only. There's nothing else for them. There's no sparsity below 100%. But in Bolt, you can specify a sparsity. It's a knob. You can choose how sparse your computations can be. And if you look at the right side picture, what we are trying to show is the carbon footprint of a model on the y-axis compared against the training time at the same accuracy. So here, if you look at Roberta model, or if you look at 3 different versions of Bolt model, one with 5% sparsity, one with 10%, and one with 20%, all of them get to the same accuracy of 93% on sentiment classification, on a particular sentiment classification data set. But then you see the carbon footprint of Bolt models and the training time is way lower than what Roberta has. So at probably 100x lower carbon emission and about 10x faster training time, we get to the same accuracy. That's how effective sparsity can be, and sparsity is. So, okay. And what are some other data sets or applications where we show, where we have shown, impressive results in the past too? So this is a 200 million parameter model trained on a Kaggle data set called Amazon 670K. This is a very standard and reliable baseline for most product search problems out there in industry. People start with Amazon 670K first. And on this data set, the blue bars here correspond to Bolt's training times. And the orange bars here correspond to TensorFlow's training time on the same CPU with Intel's one API optimization, which uses some specialized instructions also. So you can see that on any CPU, be it AMD or Intel or Apple's M1, we are about 7 to 10x faster than TensorFlow for the same network. And also you can, at the right end, you can see same TensorFlow trained on A100 GPU. So you can see that the GPU takes 1000 seconds per epoch to train, while our worst case time is 814 seconds on an Apple M1 laptop. So you can just see the cost, the price to performance ratio of Bolt versus TensorFlow on different hardware. Additionally, this is another a benchmark on sentiment analysis. This is on a data set called Yelp reviews, and we are comparing against BERT, which is one of the state-of-the-art models, and we get to the same accuracy of 93%, just like BERT, at a 100x faster training time and a 46x faster inference time. So you can just imagine how much of an energy saving this is, how much of a throughput gain this can be on tasks like sentiment analysis, intent classification, and a host of similar ones. Okay, what all of this enables is, I was mentioning about the auto-tuning capabilities and our out-of-the-box classifiers on the agenda slide. So what this, there is a hidden cost to AI that people do not really talk about. That is, we always think about how much time it takes to train a model that is already working. But to get to a working model, people tend to experiment with a hell lot of hyperparameters, which makes the training cost, which amplifies the training cost to an even more greater extent, like 5x, 10x. What we propose is our models are by default large. We can go to the extent that your CPU's memory supports. We can define a very large model and train in a sparse pattern. So for us, hyperparameter tuning is very minimal. A lot of things work by default because the model has a learning capacity that no other model out there has on a GPU. So that is where we call this a new way to go to an AutoML. That is, it's like it's fast. You don't need too many hyperparameters to tune, and you just get out-of-the-box solutions.
Yeah, hi everyone. My name is David, and today I'll be introducing something that we've spent the last few months working on, and that I'm particularly excited about, and that is a performance deep learning solution to tabular data. And this will be in the same style that Tarun just mentioned of the push button classifier type. So we'll start with an introduction, just for those who are not familiar. What is a tabular data problem? So surely you've seen some data set like this. They'll have some columns, maybe some categorical information, numeric information, and you'll have some objective, maybe in the form of a label that you want to optimize for. So the point is here that this type of data set is pervasive across several industries. This is the most common type of data. Dump it into a simple relational table. It has applications in many industries such as financial services, also healthcare, climate science, and it's even wide-reaching in sorts of like Kaggle data sets. You'll see this a lot all the time in those competitions. So the point is here that solving problems like this has wide-reaching applications in all sorts of different domains. But how do we go about solving these types of problems? So if you're familiar with, again, the Kaggle competition scene, you'll know that tree-based models like XGBoost are the standard for these problems. You'll see these types of models at the very top of the competition leaderboards. And sometimes there are some deep learning models that also reach the top, like, for example, TabNet, that have attempted to beat these tree-based models, but in general, they often fall short. And so the point is here that we set the stage that there's, for such a common model and a common problem, having this tree-based model as the top method is not ideal. And part of the reasons why are that deep learning solutions have several influential paradigms that are simply not possible with trees. For example, transfer learning, semi-self-supervised learning, and data parallel training. These things are things that deep learning is very good at, and which trees are not. And so that leads to the question, is there a wide-reaching deep learning solution to the tabular data problem? That also includes that AutoML type of capability. And we're excited to announce that with we've received some very exciting results that, enabled by our Bolt engine and enabled by our sparsity knob, we've introduced the Bolt tabular classifier. So this is a push button classifier. Everything's auto-tuned and it reaches near state-of-the-art accuracy right out of the box with minimal hyperparameter tuning. You'll see some of these results here that we've benchmarked on several tabular classification data set where we match or beat XGBoost and TabNet out of the box. And so the advantage of this is that it's much easier to train, and you get similar performances if not better than these other models. So this is promising. So another thing that is incredibly important that we've mentioned here is this sub-millisecond inference. So this right here is about 20x faster than XGBoost for single sample inference, which definitely makes an impact for downstream applications. So now that being said, let me go ahead and share a quick demo. So yeah, I'll go ahead and show you guys how easy it is to use something like this bulk tabular classifier. So let's start off by, well, I believe let's start off by downloading our data set. Yeah, so let's run this and download that. So yeah, so as we've mentioned, defining and training this tabular classifier model is incredibly easy. As you can see here, I've passed in a model size to the input, and that allows you to train with a certain size, maybe medium, small, or large, or yeah, medium, small, or large, and maybe pass in some size in gigabytes, and you can train simply by passing in the CSV file. And so we've reached about 85% accuracy in just 2 epochs in a little under 20 seconds here. So this is great. This already matches what XGBoost gets on this accuracy out of the box, or on this data set out of the box, which is great. But let's first show how we can predict on this data set, and we'll see that we've received an 85% accuracy on that on the test set, which is great again. And then just to showcase the single sample inference time, we've simply defined a list of values here corresponding to a row, and we're going to use our optimize single inference method here, and we'll show that we predicted a class in well under 1 millisecond, which is again 20 times faster inference than XGBoost for single inference. So with that being said, I'm gonna thank you guys for listening, and I'll pass it on over to Jordy, who's going to be talking about our push button sequential classifier.
All right. Yeah, once again, hi, everyone. Thank you, David, for the introduction. My name is Benito Jordy. I am one of the engineers here at ThirdAI. I've been working on data pipelines and sequential data modeling for the past few months now. And I'm really excited to finally share this with you guys in our second webinar of the year. So yeah, this is an upcoming offering called the Sequential Classifier. Just like the tabular classifier, it's plug and play, it's a classification model, but this time it leverages information from sequences of user interactions. So what kind of user interactions are we talking about here? It can range from a user watching a movie, a user adding an item to cart, a user making a financial transaction. So really just about any interaction you can think about. And just based on those examples alone, we can see that this can be very useful for applications such as personalized recommendation systems or fraud detection. Today, I'm going to focus on the first application here, personalized recommendation systems, simply because it's a very common use case. It's users basically expect that your product is smart enough to know what they need, to know what they want based on what they've done in the past. And so to have a clearer look into what this actually looks like behind the scenes, let's visit one of the example data sets. Okay, so now I'm going to print the first few lines of this data set called Netflix. Train. Yeah, so for those of you who are unfamiliar with the Netflix dataset, it's a dataset with around 100 million samples. Each sample is a rating given by one of 300,000 users to one of 17,000 movies. So if you think about the user movie matrix here, it's a matrix with about 5 billion values. A little on the, it would be very expensive to run something like singular value decomposition on a dataset of this size. Here we can take a look at the columns that we have. It's very simple. Each row only has a timestamp, the ID of the user that gave the rating, the movie ID that is being rated, the rating, the title, release date, and so on. And as the platform, your goal is to figure out, okay, based on what the user has done before, what is the next thing they're going to watch? And then you're going to give it to them on like a silver platter. You can recommend this to them and really streamline the customer journey. So one of the ways that people usually do this is through matrix factorization or collaborative filtering, as it's also known. The idea is that you calculate these affinity scores between each user movie pair, and then you retrieve the K movies with the highest scores. You can do this with our sequential classifier actually very easily. All you need to do is to define the model with the bolt.sequential classifier constructor. You tell it the size of the model that you want, and you describe the data set. So here I told the model that I want a large model, and I also have the user column in a column called user ID, and there are 300,000 unique values. I also tell the model that I want to predict movies, and there are 17,000 of them. So yeah, so this is my target. And then since this is a sequential classifier where we want to model things in the way that they appear, we also care about the timestamp. So we also pass the timestamp column there. Now we can run this right away, and this performs about as well as any collaborative filtering or matrix factorization model out there. However, since we have a deep learning model underneath, we might as well leverage the ability to digest or ingest like a rich feature set. So if our data set had more information, for example, let's say it has information about the user's bio. So we can include, let's say, static text equals user bio. You can also include multiple columns here, as you can see, as we're passing in a list. And by static, what we really mean is information that you know about a particular interaction before that interaction actually happens. So in this example, you know the user bio before any particular interaction. You can also pass in static categorical information. For example, you can pass in their favorite genres, and things like that. But in this case, since we actually don't have this information in our simple data set, we're not going to use these. What we are going to use, however, is sequential features. So to give an illustration of what this is used for, imagine I want to predict the next item. It's very useful to know the last thing that I watched, or maybe the last 5 things that I watched, or maybe the last 50 things that I watched, just to see what I'm feeling right now, what I'm into lately, because people's behaviors change over time. So let's say I want to track the last 5 movies. Then I'll just pass in the name of the column, the vocabulary size again, and then I'll pass in, let's say, the last 5 movies. I can also track multiple things at once. Maybe I want to track the last 10 movies also, and also the last 50 movies, so that I have both a long horizon as well as like I have this idea of recency. And of course, we're not limited to just tracking the target variable here. You can really track about anything. Let's say we can also track the rating. There are 5 possible ratings. Let's say we want to track the last 10 ratings to see how satisfied the user has been with their movie choices in the last 10 movies that they watched. Now we can run this right away, but due to the size of this data set and also the time constraint of this call this webinar, I won't be able to show you the whole training process, but I do have some really exciting numbers to show you. Let's go back to this. So I told you before that we have 17,000 movies. So if I want to know the next movie that a user will want to watch, then I have to choose 1 out of 17,000 movies. But of course, a user doesn't just want 1 movie. They might want to watch like between a couple of different options. So the way that we curated this data set, we took the last 10 movies of each user and put it in the test data set. The idea is that the user is interested in watching one of these next 10 movies next. So we ran a standard TensorFlow 2-tower embedding-based recommendation model. And here are the numbers we got. We chose these specific metrics, specifically precision at 1 and recall at 10, because we think it's important that you provide a good recommendation, like dead center. And also we used a recall at 10 because there are 10 labels. So yeah, we're getting these numbers. They look pretty small, but really it's just because of the sheer number of classes that you have to choose from. And this is about consistent with how sequential classifier performs without any sequential features. But if you do add sequential features, we see a huge jump in performance Precision at 1 is up by 24-fold. Recall at 10 is 4 times better. And this is simply because we now know and we can effectively extract that information about what a user is currently interested in. This really makes sense if you think about it. Let's say you've binged a lot of anime in the last 72 hours. Then you're probably going to watch another anime show instead of Titanic. Or let's say you watched Die Hard. Then it's very likely that you want to watch the next movie in the next installment in the series. All that is to say, this isn't a new idea. This is actually a proven idea. The only issue is that it demands a lot of feature engineering effort, a lot of fine-tuning, a lot of complex data pipelines, and interaction between different services. But now it's really just as simple as a single line in this API. And this single line leverages a very efficient data pipeline built specifically for our Bolt engine that also, by the way, loads everything in a streaming fashion so that it can fit your big data needs. So thank you for listening. That's it for me today.
Okay, so first, what is the problem that we're trying to solve with our out-of-the-box product search classifier? So that is a typical e-commerce problem. A typical e-commerce search engine problem is what we're trying to do. So this is a real problem that we solve with a client whose name we will not disclose in the interest of legality. When we type in a query like backyard sitting, our Bolt NLP model gets invoked and it gives products results, which when coupled with personalization gives results like a wooden table kind of thing. So basically we're typing in a query and we're expecting product results to pop up on the website. So this in this real use case, we got down the latency from like 300 milliseconds to sub 1 millisecond. Just imagine it's 300x gain on inference speed. And additionally, the state-of-the-art Roberta model gets 85% F1 score, while we get 85.4. So this is how this case study is something that our out-of-the-box product search classifier can solve for anyone who has just query to product association data. So with that, I'll just get to a quick demo of how it works on a public data set. This is how we expect our product classifier's data format is. So if you see, there is a query that I'm highlighting. It says sterling silver, genuine carnelian chip earrings. So for this particular query, these are the 3 product IDs that are relevant. Now, this data set is being pulled from a public data set called Amazon Titles 131K. It's a very popular data set. You can just look it up. So you have a query and you have its relevant products. That's all. That's all the data format that our auto classifier expects. And how does our code look like? As I mentioned, we just have about 10-15 line script that does the job for us. So we just we just import Bolt from ThirdAI. We specify our train and evaluation files. We call something called Bolt.multilabel text classifier with a number of products. The number of classes here refers to the number of products that you want to search through. And then you just train your model and you predict your model, and that's about it. We are good to go. We can simply create an inference API. We can just keep on querying this model by calling something called a predict single. That's how simple our auto classifier is, and how it works in practice. We can see, we can search through some queries. This is a real-time demo that I'm running on a machine that also runs a few other processes. So for example, this is one of the popular mysteries, unsolved mysteries, a documentary on that. You can see that when I searched for a Black Dahlia murder with a spelling mistake, by the way, it gives me first the right result. It gives me a Black Dahlia murder. Additionally, it also gives me results corresponding to Texas cadet murders and sins of the fathers, which also corresponds to all crime-related stuff. Now, additionally, if you just if you change the context to something like Clash of Swords, if you see, it suddenly gives us results about Native America and God of War chains and all of that. So you see the context is being perfectly captured with our auto classifier. And then we have, let's say we have Little Red Riding Hood. You see, we get Little Red Riding Hood and all the related products here. So this is how simple our auto classifier of product recommendation works. So as the name suggests, what is root cause analysis required for? It is primarily required in two contexts. One is either you want your network to explain why it made a certain prediction, or you want to ask your network what changes do you want to make on your input so that you get a certain desired output. Now, why is this useful? This is very useful in contexts like, say, business metrics. Like you are a company, you have certain business metrics that you are tracking, and you have a lot of input parameters that can affect your outcome. And some things are going good and some things are not going good. So how do you request an automated neural network to give you an insight onto what went wrong or what went right? So you see, that is where explainability is very important. And what our auto classifiers come with is root cause analysis baked into them. So wherever you do dot predict single, instead if you just do dot explain, you're going to get detailed explanation of what parameters led to a certain prediction or what parameters could have led to a better prediction. So just to give some example, a toy example here, it's in sentiment analysis. If we were to type in a query like, I like the movie, but I wouldn't recommend it to watch. Now, most models out there can say this is a negative sentiment. That's not very hard. But saying what made that prediction, won't recommend, is hard. That is what we solve. And additionally, we also give phrases in sentiments, not just a single token, but a phrase that dominates some other phrase and results in a right prediction. So we're going to show some examples about that. Also, in case of credit analysis, for example, just like the tabular data that David discussed, what if how does a bank make a decision on whether a certain person needs to be awarded a credit or not? There are several factors that go into credit analysis, like age, education, salary, etc. Now, how does an automated system give a decision that this is approved and also say what is the reason for the approval, or what is the reason for the disapproval? So these are the scenarios where root cause analysis is very important, and all our auto classifiers come baked in with root cause analysis. So that is that. Now we'll show a demo on how that works. So this is in the context of sentiment analysis. Let's start with a simple query. The film was good. You see, it says it's a positive sentiment, and it says was good is the phrase that was responsible. Now, this isn't very hard. This seems too simple, but let's give it a relatively complicated query where there are conflicting sentiments. The film was good, but the acting was bad. It suddenly flips the sentiment to negative, and it says there are two influential phrases, was bad and good. Both of them contribute to conflicting sentiments, but the dominant phrase was bad. See, that's how our root cause analysis module works in so much of detail. And let's again give it another query. The film was good, but I would not recommend it. Just the one in the slide. You see, would not recommend is the dominant phrase, while it counter interacts with good, but it still goes with would not recommend. So that's a very useful prediction with clear phrase detection of what causes the negative sentiment. Let's switch the context from a movie. Let's say the money is good, but the work is not. Again, we see again here, not, good, money, work, all counter interact, but the dominant phrase is not, and it gives a negative sentiment. That's it. So, okay, the conclusions that we want to draw with all our demos is, at ThirdAI, we are removing barriers for adoption. As we mentioned, we have a very performant engine that can solve a lot of problems. what we are doing now is to make things easy for people to get started, get on board with. So you can install with on any CPU with a pip install command. We have push button AI solutions that are baked into it. We have root cause analysis baked in. We can work with any budget, as in you can specify a memory budget and we can define a model at that budget. And all the challenges that we address are, first of all, we address the problem of we are not being able to train enough. Now we can train enough. You can train on more data sets. You can train more models on limited resources. The second is not being able to process data sets like sequential data or graphical data, not knowing how to use them. Now we have auto classifiers that can, directly read from the CSV files and being, be able to predict on them. We have very low inference latencies, 1 millisecond or 2 millisecond latencies on CPUs, which means you can do like your throughput can increase like 100x at no additional cost. Complex models like GPT-3 are not accessible to people. Now we are going to make them accessible to people by training large bolt models, or being able, or giving you the capability to train large bolt models on large data sets. You don't know why a certain prediction is going wrong. You can look at our explainability module and get insights into what went wrong or what went right. And of course, all of this comes at a very low carbon footprint. So with that, we will conclude this webinar.